In this precalculus algebra video, we're going to study rational functions with holes and rational functions with what are called slant asymptotes. Now, slant asymptotes are also called oblique asymptotes. So why don't we start off by graphing this rational function that has a hole in it, as we're going to see. A nice strategy when you're first graphing a rational function, as we've seen before, is to first factor the numerator and denominator. So in this case, we have f of x is equal to, it's going to be x times x squared plus x minus 2. And the denominator is going to be x minus 1. And factoring what's in parentheses, we have f of x is equal to x times x plus 2 times x minus 1 divided by x minus 1. Now at this stage, once you have it completely factored, it's nice to say what the domain is. In this case, the domain consists of all real numbers except for 1. In other words, x cannot take on the value of 1 because the function is undefined there. Now once you acknowledge that x cannot be 1, then we're going to go ahead and cancel those factors. So we're going to write this, that f of x is equal to x times x plus 2 as long as x is not equal to 1. So we're going to cancel those and we're left with x times x plus 2. Now of course the function is not just equal to x times x plus 2. You have to remember that x cannot take on the value of 1. So we're going to graph this. Now, the graph of this happens to be a parabola. So what we're going to do is we're going to graph this parabola with the assumption, or with the knowledge that x cannot be 1. So the graph of this rational function is not a parabola. It's a parabola with a hole in it, where x would be equal to, or x cannot be equal to 1. Okay, now what about intercepts? So as far as intercepts are concerned, let's look first for an x-intercept. And to find x-intercepts, what you do is you set y equal to 0. So if you set y equal to 0 here, you get 0 equals x times x plus 2. And I encourage you to find intercepts once you've already factored and canceled. So in this case, this is the simplified form of the function. And I can see that x can be 0 and x can be negative 2. So my intercepts are going to be 0, 0, and negative 2, 0. Those are my x-intercepts. And for y-intercepts, what you can do is for x-intercepts, we want to use the factored form. But for a y-intercept, it's often easier to use the original function because you can just plug 0 in for x. So for the y-intercept, you set x equal to 0. And in this case, you get f of 0. And when you plug in 0, what do you get? Well, 0 in the numerator divided by negative 1, which is equal to 0. So the y-intercept is 0, 0. Now you could have seen that from this as well, but it's nothing. It's okay to go through this process and then confirm what you had. Okay, so these are our intercepts, our x-intercepts, and this is our y-intercept, and this is the function we're going to graph. So let's go ahead and do that on the next page. So here's what we've got. Our rational function is x times x plus 2, remembering that x cannot be 1, y-intercept, x-intercepts, and our vertex. So let's go ahead and start by plotting our intercepts. So 0, 0 is a point on our graph. We also have negative 2, 0, which is going to be right there. And we've got a parabola, right? Now this parabola, x times x plus 2, has the vertex of negative 1, negative 1. You can go ahead and find that by using the vertex formula x equals negative b over 2a when you put this in standard form. So when you do that, you'll find that you get the vertex right there. And we have graphs, or we have videos on parabolas as well. Now that parabola is going to look like this, but there's one thing to remember, right? And it's that x cannot be 1. The graph of this is not a parabola, as we talked about. It's a parabola with a hole in it. So when x is 1, that is 3, right? So if I plug in 1, I get 3. 1, and this is 3, and 3 times 1 is 3. So if I go up 1, 3, I have a big hole right there in my parabola. So right there. So I'm going to graph the parabola with that hole in it. Let's go ahead and do that now. So there would be our graph of this rational function. It's a parabola with a hole in it at 1, 3. Okay, so other rational functions have what are called slant asymptotes. Let's go ahead and look at those. So a slant asymptote, this is the solid curve here you see is the graph of the rational function. And this rational function actually has two asymptotes. The first asymptote we've seen before. This one is a vertical asymptote. We saw that in a previous video. What's new is this, what's called a slant or an oblique asymptote. different textbooks use different names. Okay, so a slant asymptote is a line. It's the line y equals mx plus b. Now it's a line that the curve is getting closer and closer to as y goes to infinity, or sorry, as x goes to infinity and as x goes to negative infinity. So the y-coordinate is getting closer and closer to the y-coordinate of this line. Note that when you have a slant asymptote, you don't have a horizontal asymptote, right? Because, or in that direction, because this occurs as x goes to infinity. So if as x goes to infinity, it's approaching this line with a non-zero slope, then it can't also be approaching a horizontal line, which is what a horizontal asymptote is. So now, a function has a slant asymptote if the following is true mathematically. If y gets closer and closer to mx plus b. Now this is the y of the function. If the output of the function gets closer and closer to mx plus b as x goes to positive or negative infinity, okay? In that case, we say y equals mx plus b is a slant asymptote. And we'll see an example, of course, of this in a minute. Now, the thing to remember about rational functions is that rational functions have slant asymptotes. This is a rule that you can always use. Rational functions have slant asymptotes if the degree of the numerator, so the degree of the polynomial in the numerator, is one more than the degree of the denominator. That's our rule. That's how we're going to know we have a slant asymptote. So find the slant asymptote and the vertical asymptotes, or asymptote if there's only one, and graph this function. Okay, so why don't we start off with first finding intercepts. The problem didn't ask us to do it, but it's always nice to have those. So for intercepts, let's start with the x-intercept. And for the x-intercept, you want to set y equal to 0. Oh, by the way, we mentioned that with rational functions, we like to factor them first. So it's x times x plus 2, and then divided by x minus 1. So this is our go-to when we have a rational function. And to find the x-intercepts, you set y equal to 0. And so setting the y-coordinate equal to 0, we get 0 is equal to x times x plus 2 divided by x minus 1. And this is true when x is 0 and when x is negative 2. So our x-intercepts are going to be 0, 0, and negative 2, 0. Okay, now let's go ahead and find our y-intercept. So the y-intercept, that's going to occur when x is 0. So we'll plug 0 into the original function and we get f of 0, and you can see what it's going to be, just like before. So it's going to be 0 over negative 1, or just 0. So the y-intercept, of course, is 0, 0 as well. Now, this function also has a vertical asymptote, right? So we can think about vertical asymptotes. Let's write that over here. Now, if you remember from previous videos where vertical asymptotes occur, what you do is you look at the rational function in factored form, and if you've already done all your canceling, if there's canceling to be done, in this problem there's no canceling to be done. So if after your canceling there's a place where the denominator is 0, that's a vertical asymptote. So the vertical asymptote for this function is going to be the line, the vertical line x is equal to 1. Now what about horizontal asymptotes, or slant asymptotes? Now to find slant asymptotes, what you do is this. You go back to the original function and you use long division to divide the denominator into the numerator. So you divide x minus 1 into the numerator, which is x squared plus 2x. Now I can see right away that I'm going to have a slant asymptote because the degree of the numerator is 2 and the degree of the denominator is 1. And so the degree of the numerator is 1 more than the degree of the denominator. So when you do this long division, well, we're going to multiply x by, it's going to be x, and we're going to get x squared minus x, and then we're going to subtract that off, just like we know how to do long division. That's going to be 3x, and then we can multiply by 3, So it's going to be plus 3 in the quotient, and then we get 3x minus 3. We subtract that off, and we're left with subtracting off just 3. So we end up getting, upon doing long division, we get x plus 3, right, the quotient, x plus 3, plus 3 divided by x minus 1. So what we found is that we took x squared plus 2x, divided it by, let's write that here, we took x squared plus 2x, and we divided it by x minus 1 using long division, and we got this, x plus 3 over x minus 1. Now what's important, the reason we do this is that I can see that as x goes to infinity, right, because that's what we're considering when we're looking at slant asymptotes. As x goes to infinity, what happens to this? Well, the x is getting large in the denominator, but the 3 is remaining the same. So that is going to 0 as x goes to infinity or negative infinity, right? Isn't that going to 0 because the denominator is getting large? And what happens is that this function is heading to x plus 3 then as x goes to infinity or negative infinity. That is why we write this, is going to x plus 3 as x goes to infinity or negative infinity, okay? And what that means is that x plus 3 is a slant asymptote. That's the criteria for being a slant asymptote. So the slant asymptote is going to be y equals x plus 3. So this function has a vertical asymptote, x equals 1. It also has a slant asymptote of x plus 3. Okay, let's go ahead and put this all together on the next page and go ahead and graph this rational function. So here's our information. We have intercepts at 0, 0. Let's graph that. Plot that point. We have one at negative 2, 0. And we have a vertical asymptote x equals 1. Let's go ahead and draw that in first. So there's my vertical asymptote. And I also have this slant asymptote, the line y equals x plus 3. Now to graph that, this is a line, right? It's got an x-intercept at negative 3 and a y-intercept at positive 3. So that slant asymptote is going to go like this. Let's go ahead and graph that in now. Okay, so there's our slant asymptote. Now let's go ahead and write the function here as well in factored form. It was y equals x times x plus 2 times, divided by rather, x minus 1, I think it was, yeah. Okay, so now notice that as x goes to 1 from the right for the vertical asymptote, from our video on graphing rational functions part 2, we see that x goes to 1 from the right, the numerator's going to, it's a positive number, and the right-hand side, or sorry, the denominator is going to 0 but through positive values. So the graph is going like, as you approach 1 from the right, the graph is looking like this. It's going up like that, okay? And then the slant asymptote as x goes to infinity, the graph is getting closer and closer to the line. So it's looking like that. So this is the combination of those two behaviors, going to infinity as you approach the vertical asymptote and then approaching the line the other direction. And then likewise, as you approach 1 from the left, the graph is going to negative infinity. So it's going to go negative infinity through that point, come back, and then approach the line. So the graph is going to look like this, okay? So let's go ahead and graph this branch in, and we'll go ahead and make that branch a little clearer as well. Let's do that now. So this would be our graph, right? So what I see is that we have two branches. The first branch, I see that it goes to negative infinity here, and then it's approaching the slant asymptote as we talked about. And then as x approaches 1 from the right, we're going up to infinity and then approaches the slant asymptote as x goes to positive infinity. Okay, so that's how we graph special rational functions that have holes or slant asymptotes. Until next time.